Okay, so welcome to Math 349 Operations Order. So this is the 5th class. And what I want to do today is talk about the first really non-trivial, non-commuting relationship you've probably seen. Subtraction, division, everyone has seen that. That doesn't commute. Okay, that's not a big deal. Matrices are far more interesting. And what I want to do today is talk about the thought process as to how would we find all matrices that commute with A. And then the next, why would we care about finding matrices that commute with A? We can study almost anything we want in mathematics. The question is, which things are we studying that are useful? So whenever you are doing something like this, there's multiple ways in which you can go. You can start off by doing the application first, and then saying, this is the problem that motivates everything. We want to understand this problem. And then to solve this, we now need to develop some theory. Or you can develop the theory first and go from the theory to now what can we do with this? How many of you have ever heard of Faraday's quote about his discoveries in electricity? So he was asked after some of his theoretical discoveries, well, what good is any of this? And the versions I've heard is here that says, well, what good is a newborn baby? Or in 20 years, you'll be taxing it. We don't necessarily know what the value of it is right now, but there is something to be said for generating theory and then seeing what we can use it to. A lot of mathematics, it often takes a couple of decades to a century or two before we find a place where it is of use. General relativity, if anybody here does physics, used crucially a lot of differential geometry from the 1800s. And it found a nice home for all the mathematics that was developed there. The reason I want to do the theory today was just to really iterate, talking about the thought processes of how do we attack something. So we're trying to find matrices that commute with A. And so let's look at the 2x2 case. So, find all 2x2, whoa, somehow switched, all 2x2. It's almost surely this. Let's leave from the rain. All right, all 2x2 matrices B commuting with a fixed 2x2A. So we want AB equals BA. And we talked about first trying to do this by restricting to special cases of A. See if we can solve for that, and then keep pushing forward, keep pushing forward, keep pushing forward. And sometimes what you can do is you can say, well, actually, I solve it for this class of objects. And then a more general class, I can do maybe some kind of transform and reduce it to this. So what's the first class of matrices that we want to study? The easiest case you can think of. A is 0, more generally than 0. 0 is a special type of this matrix family. I'm sorry? Well, I want to look at all B. So I'm trying to find all B that commute with A. So the identity. And we could actually do it. So the 0 and the identity. What family do 0 and the identity both sit in? Diagonal, but there's something smaller than diagonal that includes the identity in the 0 matrix. Triangle is actually bigger than diagonal. Symmetrical is bigger. So what's smaller than diagonal, but would include the identity in the 0 matrix? So a diagonal matrix would be, say, A, 0, 0, B. Right? So diagonal, let's use the letter D, would be, say, of the form D1, 0, 0, D2. There's something a little bit smaller than diagonal that would include the identity and the 0 matrix.
D1, 0, 0, D1.
Excellent. So let's do multiples of the identity. So let's do D0, 0, D equals D times the identity. So this is a smaller space of matrices than diagonal matrices. And this is going to be a much easier space to study. So if we want to study multiples of the identity, well, let's look at B times DI is equal to DBI, right? But what is B times I? It's just B, or we can write it as just B, that's fine. And how else can we write B? IB. So this is D times IB. So all B commute with D times I. So if you're multiples of the identity, every matrix commutes with you. It's really not that big of a deal. So then the next question would be, what if we study diagonal matrices? So now, let's study diagonal. And is every matrix equivalent to a diagonal matrix? And that means does there exist a matrix S such that S inverse AS is diagonal, D1, 0, 0, D2. So if every matrix can be diagonalized by a change of basis, then maybe what we could do is the following. Look, change the basis of A and B so that in this new basis, A is diagonal. And then if we can prove things for diagonal, we would then know things for everything. Does anybody remember linear algebra well? It's a dangerous question to ask. So can every matrix be diagonalized? So unfortunately, not all matrices are diagonalizable. But all are triangularizable. I think that's a word. So I can always put a matrix into upper triangular form by doing a change of basis. But I can't guarantee that the matrix will be diagonal. How many of you have heard of Jordan canonical form? Okay, so if you've heard of Jordan canonical form, that's great. So for example, consider something like 1, 1, 0, 1. This cannot be brought into diagonal form. If a matrix is diagonal, how many eigenvectors does it have? So if I give you a 2 by 2 diagonal matrix, how many eigenvectors does it have? 2. And so, for example, say A equals D1, 0, 0, D2, eigenvalues D1, D2 with eigenvectors. So what would be the corresponding eigenvectors for D1 and D2?
The D1, 0.
Yes. Yes, but you would almost never write it as D1, 0. Nope. So if I have an eigenvector, I can multiply it by anything that's non-zero and it's still an eigenvector. So I wouldn't have the first component be D1, I would have the first component just be 1. So I would normally choose the eigenvectors to be 1, 0, and 0, 1. So this matrix would have 2 eigenvectors and 2 eigenvalues. Okay. If I give you the matrix 1, 1, 0, 1, we could ask how many eigenvectors and eigenvalues does this have? So for A equals 1, 1, 0, 1, eigenvalues are, so who can tell me what the eigenvalues are for this matrix? Almost, I'm asking for the eigenvalues. So the eigenvalues are numbers. So what would the eigenvalues be? Just 1. How many times is 1 an eigenvalue? What's the multiplicity of 1? So we solve determinant of A minus lambda I equals 0 to find the eigenvalues. Or we need 1 minus lambda, 1, 0, 1 minus lambda equals 0, or 1 minus lambda squared equals 0. So lambda equals 1 and 1. So 1 is a repeated eigenvalue. You can then go through and you can show that this matrix does not have two distinct eigenvalues. All the eigenvectors, all the eigenvectors of this matrix are going to be along the x direction. So if we now try to solve, AV equals V, that leads to 1, 1, 0, 1, xy equals xy. So we get x plus y, y equals xy. Oh, sorry. Yes. And so what's the only solution to this? One zero. Or you can do, or just x 0, but yes. So this implies y equals 0. Else x plus y cannot equal x. So all eigenvectors in the direction 1, 0. So this matrix only has one direction for its eigenvectors. And so with a little bit of work, you can show that this matrix can't be diagonalized. Because if it could be diagonalized, if I could find some matrix S such that your S inverse AS is this diagonal matrix, how many eigenvectors does this have? It has 2. And then you can show by going through things that you would then be able to find 2 eigenvectors for A by just multiplying by S and S inverse and just pass things around. So with a little bit of work, and it's not bad if you want to review your algebra, to try to show that this will imply A has 2 different directions. And since we know that A doesn't have 2 different directions, it can't be diagonalized. So there do exist matrices that cannot be brought into diagonal form. So when we're trying to understand what's going on, it's not enough to understand the problem for all matrices A that are diagonal. That's going to miss matrices. It turns out we can convert every matrix to upper triangular form. And if we can study that, that's great. Okay. So let's continue. So let's assume we have a diagonal matrix. So let's assume A equals D1, 0, 0, D2, and maybe B is equal to A, B, C, D. So how would you try to find all the B that work? What thoughts come to mind? So find all B such that AB equals BA. We want to try to find all the matrices that commute with A. So what can we do next?
The other in general terms, you could multiply them.
Yeah. Yeah. Roll up your sleeves, just do the algebra, right? We've simplified things a little bit by saying, look, our matrix A now has 2 zeros in it. So let's actually compute. So we would have, oops. So we would have D1, 0, 0, D2. Oh, this is not going to be good notation. Well, it's fine. A, B, C, D versus A, B, C, D, D1, 0, 0, D2. And let's start multiplying things out. So catch me if I make a mistake. I think it's going to be AD1 for the upper left, and then BD1. Yes? Okay, and then for the bottom row, it's going to be CD2. And then DD2. right, now when we come over here, it's going to be AD1, and then BD2, and then CD1, and then DD2. Okay, so which are the challenging parts? So CD1. So what does CD1 have to equal? CD2. Anything else I have to worry about? Okay. So this gives me some constraints. Are there anything about A? Anything about D? A and D are free. All right, so this is a good start. So we already have some understanding of what's going on. Can somebody give me a simple choice of C and B that you know will work no matter what D's I choose? Yes.
0.
Yeah, 0. So if you take B and C to be 0, then you make B a diagonal matrix, and you get diagonal matrices commute with diagonal matrices. Okay, not surprising. So as a special case, if B equals C equals 0, all good, diagonal commutes with diagonal. If, however, we don't take B and C to be 0, then we need to know things depending on D1 and D2. So what must be true if we want CD1 to equal CD2? I'm sorry? Right. So in general, CD1 equals CD2 implies C equals 0 or D1 equals D2. And then BD1 equals BD2 implies B equals 0 or D1 equals D2. If D1 equals D2, then anything is fine for B and C. Well, if B1 equals B, I'm sorry, if D1 equals D2, our diagonal matrix reduces to a multiple of the identity, the case we've already handled. So it's not surprising then that everything works. If D1 does not equal D2, then we would get both C has to be 0 and B has to be 0. So we have a complete analysis in the case when our matrix A is diagonal. With a little bit of work, you can show that this works if the matrix can be diagonalized. So if it's not initially diagonal, but if I can change basis and make it diagonal, that's fine. And what's really going on is, let's say I give you a matrix here, A and B, and consider S inverse AS and S inverse BS. So look at AB and BA versus S inverse AS, S inverse BS, and S inverse BS, S inverse AS. So let's see what happens, when you look at S inverse AS, S inverse BS, how does that simplify? Yeah, the middle S's cancel. And so this is just S inverse ABS and S inverse BAS. So if A and B commute, then S inverse AS and S inverse BS commute. Conversely, if these matrices commute, you should be able to get that A and B commute. So I'll leave you to think about that, but the idea here is you try to reduce to a simpler case, analyze that case, and then see how far can you push it. And so if the matrix can be diagonalized, then we can basically solve it very nicely. Once we find the matrices that commute with a diagonal, we can then just change back to a basis system. Do you think the universe cares how I orient my coordinate axes? Can you prove it? That's way beyond my pay grade. Right? It is possible that the universe does care about how we choose to orient our coordinate axes. I would be shocked. Right? The laws of the universe should not depend on how we choose to write things down. And so all of linear algebra is trying to find what is the most convenient coordinate system for the problem that you're looking at. And so again, this does not fully solve the problem. This only solves the problem for matrices that are diagonalizable. Now, almost every matrix is diagonalizable. It turns out if the eigenvalues are distinct, then the matrix is diagonalizable. With probability 1, if you write down a generic matrix from the real world, it will have distinct eigenvalues and it will be diagonalizable. Unfortunately, whenever you look at anything coming from math, there could be something very special. Can somebody give me matrices? Determinant. What's the determinant of the 1 by 1 matrix 1? Its determinant is 1. What's the determinant of matrix 1, 2, 3, 4? You get 2. Negative 2? Yep. What about the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9? Does anybody know the determinant of this matrix? Goes 1, negative 2, so it's positive 3, right? It's 0. What matrix should I look at next? 4 by 4. How should I do it? Yep, so
4, 5, 6.
So good. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I assume you can all do determinants in your head. Carry the 3, 0. Anybody want to conjecture? Do you want more data? I'll do one more. All right, this is going to take me a little bit longer because this is 5 by 5. Zero. Are you surprised that these matrices all have determinant 0? Something should be going on, right? If you're getting 0 this many times, something has to be going on. What I love about this is you don't start off with 0. So for small values, the limiting behavior hasn't kicked in yet. I have a paper here with Professor Goldmacher back from when he was an undergraduate, where we were trying to look at something. And we found that the first 7 moments of what we looked at agreed with the first 7 moments of the semicircle distribution. And there was a reason to expect the answer might be the semicircle, but in the 8th moment it differed. And so sometimes things can persist for a while before you go far enough to have enough freedom to see what's going on. So as a nice way to review a little bit of your linear algebra, what does it mean if the determinant is 0? So one consequence is one of the eigenvalues must be 0. What does it mean to have an eigenvalue of 0? Not linearly independent. Other one. Linearly dependent. So it means that the columns or the rows are linearly dependent. Or if you look at the volume of the parallel pipette or whatever you want to call it in dimensions, that has to be 0. because the volume is essentially the product of the eigenvalues. And so what this means is that once you look over here, there should be some kind of dependency among the columns or the rows. I will just make this 7 actually look like a 7. So I'll leave it to you to try to figure out what kind of dependence do we have among the rows or the columns. And why does that dependence not kick in until we get to at least a 3 by 3? But whenever you see something like this, there's usually a story going on. Why am I talking about this? Just because of, we just proved something for any matrix that's diagonalizable. Almost every matrix is diagonalizable. So in some sense, we're in great shape. Because almost every matrix is diagonalizable, we know what to do for any matrix that's diagonalizable. Unfortunately, the matrices we care about from the problems we're studying might not actually be diagonalizable. If you have any real-world data, it would be shocking for things to be set up for it to be perfectly zero. But if things are coming from number theory or from combinatorics and you have integers, then it is possible that things could catastrophically align and you could get zero. And so I'll leave it to you to think about what would happen if you had an upper triangular matrix. And then, of course, this is only the analysis in the 2 by 2 case. What happens when we go to higher dimensions? I'm going to skip that for now. That was a subliminal message. All right. So let's say I want to look at a pair of functions. Maybe I'll use v of x to be the vector f of x, g of x, or do you want to do v1, v2? Which do you prefer? v2? We can do that. So we will go backwards. So we have v1 of x, v2 of x. And I want to have A is a 2 by 2 matrix. I want to study v prime of x equals a v of x. So this is a differential equation. So this is the same as v1 prime of x, v2 prime of x equals a, b, c, d, v1 of x, v2 of x. How many of you have taken a class in differential equations? How many of you have seen some differential equations before? You should have seen some simple differential equations in probably Calc 2. This is the challenge where if you did this in high school, it may or may not have been covered. Does this look like any differential equation you've seen before? V prime of x equals a v of x. Does this look like any differential equation you've seen? Okay, which one? Can you say it again? Well, aren't rabbits hairs?
A rabbit or a hare and some other animal.
So I mean, it could be like rabbit and fox. And so something like this could be modeling, a rabbit population and a fox population. So the more rabbits you have, the more foxes can exist. But of course, the more foxes you have, the more rabbits are killed. But does this remind you of any one-dimensional differential equation? So instead of using v prime, I should use what? Well, not a. I've got to somehow give me a one-dimensional differential equation. What should I use rather than v prime? There are two things that are acceptable. Y. So this would be the same as y prime of x equals a y of x. How do we solve that? So what's the solution to y prime of x is a y of x? We've talked about this, I think, last week. I'm sorry? We could integrate. So we have dy dx equals a y of x. So dy equals a I'm sorry, dy over y equals a dx. Integrate both sides. And this leads to what? So what's the integral of dy over y? It's the natural log of y is ax plus some constant c. So if the natural log of y equals ax plus c, what does y equal? E to the ax plus c, and I can write that as some constant, I'll call maybe c tilde, e to the ax. When I'm solving differential equations, I often need to give you the initial condition. It's not enough to just tell you y prime equals a y of x. You know, if I tell you your speed at every moment in time, can you tell me where you are? What else do you need? Which position? And actually, it doesn't have to be initial position. Any position, right? If I know where you are after 3 hours, well, I know how much I've moved in 3 hours, so I can extrapolate back to see where did I start from. I need one piece of information. You know, I need my location at one point in time. Normally, we give it at the start, but I can give it to you at any point in time. So over here, anything of this form is going to work. It is inexcusable to have the wrong answer for an integral. It's okay not to know how to do the integral. That's fine. But it is inexcusable to have the wrong answer. Why is it inexcusable? You can take the derivative. And so if we take the derivative here, we get y prime of x is going to be c tilde e, that's going to be a e to the ax, which is just a c tilde e to the ax, which is just a y of x, which is what we wanted. So we see that this actually does solve the differential equation. So we know y of x equals c tilde e to the ax solves y prime of x equals a y of x. We want to solve v prime of x equals a v of x. Can anybody give me a conjecture as to what the answer might be? It's okay if the process may not be legal. How would you generalize the solution? Okay, so I plug in, what do I plug in? Good, so v of x equals, you know, my constant time. So can I multiply a matrix by a scalar? That's legal. Can I raise the number e to a matrix? Why? Have you ever raised a matrix? Have you ever raised the exponential to a matrix before? No. So the question is, what the hell would that even mean? Right? I understand what it means to raise 2 to a power. You know, 2 squared, 2 cubed, 2 to the 4th. I understand that. I understand what it means to take a square root. If I want to find the square root of y, I'm looking for number x such that x times x equals y. So I can understand square roots in terms of standard multiplications. That's not a problem. What if I want to raise something to the root 2th power? What does it mean to take, you know, say 5 to the root 2th power? Does anybody know how you would calculate 5 to the root 2th? So there's a lot of things that have been, I think, glossed over in your math education. I know precisely the weak points in calculus and whatnot. Have we? I'm sorry? No, because 5 to the 2 to the 1/2 would just be 5. So if you give me 5 to the root 2 versus 5 squared to the 1/2, is that what you were saying? Two to the 1/2 like this. Right, but that's the same as writing it as 5 to the root 2. So we need a way to interpret what is 5 to the root 2. So one possibility is you could do a string of rational approximations, and you could try to make that work. Let's do a calc review. So let's find some derivatives. So I'll give you the function x cubed, x to the 3/2, x to the root 2. What's the derivative of x cubed? 3x squared. What's the derivative of x to the 3/2? 3/2 x to the 1/2, and the derivative of x to the root 2. So even though we don't even know what x to the root 2 is, we at least know what its derivative is. All right. And so the rule is the derivative of x to the r is r x to the r minus 1. So the question is why? So does anybody know how we actually prove the derivative of x cubed is 3x squared? So go back to your calculus class. How do we prove the derivative of x cubed is 3x squared? Okay, so we went all the way back to the limit as h goes to 0 of f of x plus h minus f of x over h, and then use the binomial theorem. X plus h cubed is 3x cubed plus 3x squared h plus . We actually don't even need the full force of the binomial theorem. We just need to know the first two terms. So that's how we can calculate the derivative of x cubed. How about x to the 3/2? We can't argue with this as f of x plus h minus f of x over h, because we don't know how do you expand x plus h to the 3/2 power. Now, there's a couple of things we could do. So option 1, x plus h to the 3/2 minus x to the 3/2 over h. There are two things you need to learn how to do in mathematics. You need to learn how to do nothing two different ways. Can somebody tell me one way to do nothing? Add 0. The other way to do nothing. And for cultural extra credit, the TV show about nothing. Thank you. Yes, I feel better. I would be very upset if nobody got Seinfeld. So we multiply by 1. All right? So we're going to multiply by 1 by multiplying by x plus h to the 3/2 plus x to the 3/2 over x plus h to the 3/2 plus x to the 3/2. And if we do that, then as we continue, we'll get x plus h cubed minus x cubed over h times 1 over x plus h to the 3/2 plus x to the 3/2. As h goes to 0, this goes to 1 over 2 x to the 3/2. As h goes to 0, goes to 3x squared. So that's one way to do this problem. Okay, so I was able to do a very clever multiplication But what if I gave you 7/13? Would you still be able to do something like that? Maybe the algebra might be a lot worse. There is a second option. Option 2. If f of x is x to the 3/2, g of x equals f of x squared is x cubed, g prime of x is going to be 2 f of x, f prime of x is 3x squared. So if I know how to do x to an integer, I can actually get x to a rational by just raising my function to that power. And now I have this function g, which is f squared, which is x cubed. I can now take the derivative. All right, last one. X to the root 2. The way you do this is you note x to the root 2 is e to the root 2 natural log of x. Use the chain rule. Okay. How many of you saw this for the proof of x to the r when you took calculus? This is a little scary. How many of you knew the derivative of x to the r is r x to the r minus 1? So most of the time in calculus, they just prove the first one. And then somehow they slip in that we're going to use this for all exponents, but they really don't tell you why. The reason I wanted to cover this at some point in this class is how easy it is to make an accidental assumption and not even be aware that you're doing it. And so you've got to be very careful. The proof is extremely difficult. You need to understand the exponential function, the logarithm function, you need the chain rule. And so what we really need is e to the x is defined to be the sum, n goes from 0 to infinity, of x to the n over n factorial is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. And this converges for all complex values of x. And so the denominators are growing so rapidly with the factorial that this will converge no matter what value of x you put in. Okay? Now, what is e to the x times e to the y? Yes, but we don't know that. Technically, what we have is this is the sum, n goes from 0 to infinity, x to the n over n factorial, times the sum, m goes from 0 to infinity, of y to the m over m factorial. Now, with a little bit of algebraic rewriting, this is the same as the sum, let's say, k goes from 0 to infinity, the sum L goes from 0 to k, x to the L, y to the k minus L over L factorial, k minus L factorial. So you have to justify that you can group the terms however you want. The rapid decay allows you to do this. What I'm basically saying is, look, when I multiply the x's and the y's, I'm going to get some power of x times some power of y. Let's group all the terms where the sum of the powers of the x and the y add up to k. So if I have L copies of x, I have k minus L copies of y. Is everybody comfortable with this? So, it would be, if I want k equals 0, it would just be 1 times 1. If I want k equals to 1, it'd be x over 1 times y, times 1 plus 1 times y over 1. If I want k equals 2, it would be x squared over 2 factorial times 1 plus x over 1 times y over 1 plus 1 times y squared over 2 factorial, and so on and so on and so on. So I'm just grouping all of the pieces together so that the power of x plus the power of y equals k. When you see L factorial and k minus L factorial, that should look a lot like an object you've seen before. What does that look a lot like? Yeah, What am I missing to make it a nice combinatorial thing? Yeah, what do I want in the numerator? I want a k factorial. So I have to put a k factorial down below. So this is the same as the sum. K goes from 0 to infinity. I can pull the 1 over k factorial out because it doesn't depend on L. And I'll have a sum. L goes from 0 to k of k choose L, x to the L, y to the k minus L. Well, by the binomial theorem, that's the sum k goes from 0 to infinity. This is going to be x plus y to the k over k factorial, which is e to the x plus y. So it is e to the x plus y, but it was non-trivial to prove it. If that was not the case, this would be horrible notation to call this e to the x. But this is the definition of e to the x. It works for everything. So what I want you to think about for the next class is, what would happen if I, instead of putting in a real number x, what if I put in a 2 by 2 matrix? Would this series expansion still exist? Would the series expansion still converge? Again, it's initially defined only for real numbers. And this is going to lead to why we actually care about trying to find which matrices commute with others. And this is a nice way to review some of the things you should have seen in earlier calculus classes. All right, so this is a good place to stop.